Section 4.2 is about selections and arrangements. A selection problem involves choosing a subset of elements from a given set. And an arrangement problem involves choosing a subset and then putting its elements into some particular order. An arrangement has two properties. First, the order of the elements matters. And two, all of the elements are distinct. An example of a permutation would be one where Yifan has 26 refrigerator magnets in the shapes of the letters from A to Z. How many different three-letter strings can he form with these? So this is a bit of a different question than I was asking in section 4.1 because there are only 26 physical refrigerator magnets. So once I make a selection for the first blank, if you want to call it that letter can no longer be used because I only have one magnet for each letter. So you still can think about it like a string of 3 blanks. I have 26 options for my first letter, but like I said, once I make a choice, that choice can't be chosen again, so there's only 25 for the second blank. And then once I've chosen both of these, I've used 2 of my 26 magnets, so there's only 24 options for the third blank. So I will multiply 26 times 25 times 24, and there are 15,600 options here. The arrangement principle says the number of ways to form an ordered list of R distinct elements drawn from a set of N elements is P of N comma R, where we multiply N, the total number of elements in the set, so N times N minus 1 times N minus 2, and so on until we get to N minus R plus 1. So for example, in our last problem, there were 26 letters to choose from, and I wanted to make a string of length 3. So I started with 26, and then 26 minus 1 is 25, and then 26 minus 2 was 24, and that's where I stopped. I stop at minus R, so it would be 26 minus 3 is 23, plus 1, so I stop at 24. The notation P of N comma R comes from the mathematical term for arrangement, which is permutation. And we can use factorials to represent these formulas. Recall that a factorial, so N factorials, that exclamation point, is equal to N times N minus 1 times N minus 2, all the way down till you get to 3 times 2, and you always end with 1. By convention, we define 0 factorial to be 1. So I know that doesn't fit the formula that we've given, but we just define it that way. 0 factorial is defined to be 1. And then we can write our formula for permutations using factorials. So P of N comma R is equal to N factorial divided by N minus R factorial. And I would write that down for sure. So let's look at an example. A baseball team has a 24-man roster. How many different ways are there to choose a 9-man batting order? So batting orders are an ordered set. Once we choose a person to bat first in the lineup, that person cannot be chosen again. We have one fewer option. So we want to fill in these 9 blanks, treating them like this person will bat first, this person will bat second, and so on. So if there are 24 people on the roster, I have 24 choices for the first blank. But once I make a choice, then there's 23 people left to choose from, then 22, then 21, and so on. And think about what number I would have to end with if there are 9 people in this batting order. And the answer is 16. I would multiply 24 times 23 all the way down until I get to 16. And there are over 474 billion choices for this batting roster, which is humongous. But if we want to put this into the formula, the number of people we had on our roster was 24, and we're trying to make a list of length 9. So N is 24 and R is 9. And I can write P of 24 comma 9. Filling into our formula, that means I end with 24 minus 8, which is where that 16 came from. I can also use factorials. If I use factorials, it would be 24 factorial divided by N minus R. So 24 minus 9, which is 15 factorial. And when you write these numbers out, it turns out that the 15 times 14 times 13 all the way down to times 3 times 2 times 1, this whole factorial cancels off the 15 factorial that I had on top, which is why it stops here at 16, the way we wanted it to. And if you type this in your calculator, I'll show you when we get to class how to find the factorial button if you don't already know. But you can type this in your calculator and it gives you the same number, 474 billion plus. Combinations. An example of a combinations problem would be a baseball team has a 24-man roster. How many different ways are there to choose a group of 9 players to start the game? So instead of batting first, maybe we're sending our players to the outfield first. So we just need 9 players to start the game. We don't care about what order they're in. We just want a group of 9. This type of choice is called a selection because the group is an unordered set. The selection principle says the number of ways to choose a subset of R elements from a set of N elements is C of N comma R is equal to N factorial divided by R factorial times N minus R factorial. So if you compare this formula to the formula for the permutations, you'll see there are less options here because we're dividing by R factorial. When you read C of N comma R, you actually read it as N choose R. And the other notation for that is this kind of column vector. It looks like a parenthesis with N over R. So we read this as N choose R. The key distinction, and this is very important, in arrangements, the order of the elements in the subset matters, and in selections, it doesn't. So let's go back to our example. A baseball team has a 24-man roster. How many different ways are there to choose a group of 9 players to start the game? So N is 24 and R is 9. But this time we'll plug into our combinations formula, 24 factorial divided by 9 factorial times 24 minus 9, which is 15 factorial. You can type this in your calculator, and there's only a little over 1 million options, as opposed to the massive number we got last time. Now let's just look at some cool mathematical examples of how this could be used. we could answer questions like, how many solutions are there to the equation x1 plus x2 plus x3 plus x4 plus x5 equals 13 if our x's must be non-negative integers. So non-negative means we can have 0, we can have 1, 2, anything up to infinity. So non-negative integers. And we think about breaking down 13 into units, into ones. So 13 is the same thing as 1 plus 1, 13 times. And so the solution amounts to dividing up strings of ones into 5 different groups. For example, if we take 1, 1, 1, 1, and then we use a vertical line to separate that group, then I've got an empty space and another vertical line, so no ones right there. And then 1, 2, 3, 4, 5 ones and another vertical line, 1, 1 and another vertical line, and then 3 ones. That means my groups are 4, 0, 5, 1, and 3. So that corresponds to the solution x1 equals 4, x2 equals 0, x3 equals 5, x4 equals 1, and x5 equals 3. If I add those numbers up, I do get 13, so that is one solution to the problem. So each set of solutions depends on arranging the 13 ones and the 4 dividing lines that we use to group those ones for a total of 17 different symbols. And if we want to choose 4 groups, the leftover symbols will form the 5th group automatically. For example, if I had already chosen to use the 4 ones, a division line, 5 ones, a division line, 1 1, and a division line, these extra 3 leftovers formed the 5th group automatically. I didn't have to choose another symbol there. So we are taking 17 symbols and choosing 4 groups. So the problem can be solved by evaluating 17, choose 4. And it turns out there are 2,380 solutions to this problem. Kind of cool. In high school, you learned to expand binomials. So you did things like a plus b squared, which was a plus b times a plus b, and you FOILed. So a times a times b times a, b times b, and you combine like terms, and you get this quadratic. You could do a cubic, but you would have to FOIL again, all these things, and you would get lots of terms. There's actually something called the binomial theorem that says let j and k be non-negative integers such that j plus k equals n. The coefficient of the a to the j, b to the k term in the expansion of a plus b to the n is c, or the combination n choose j. So for example, the coefficient of a squared b in the expansion of a plus b to the 3rd power is c, or I keep saying that, is 3 choose 2. And if we plug in 3 choose 2 into our formula, it would be 3 factorial divided by 2 factorial times 3 minus 2 factorial. And if we multiply out all those numbers, we see that the coefficient of a squared b is 3, which is the same thing you get if you FOIL or distribute as you did in high school. So you can write this binomial theorem down, but we will definitely work with it in class, and I will not ask you to recreate this on the quiz. But it's something cool to look at, and it's one of the biggest theorems of mathematics. So I will help us break this down when I see you in class next time.